Hello, my name is Valeria Saldaña, and today I'm going to be walking through key concepts of currying, collections, and callbacks, and abstract data types. Here's an outline of what I'll cover today. First, I'll discuss currying, understanding how and why it is used. Then, I'll go through collections and callbacks, focusing on operations like map, flat map, and folds. And lastly, I'll dive into abstract data types, including map, set, and parallel and distributed collections. Let's start with currying. Currying is a process of transforming a function with multiple arguments into a chain of functions, each taking a single argument. This is incredibly useful for partial application. Here's an example. When we call add curried 3, it returns a new function, 3 plus something else. And then when we call this return function with 4, it gives us a final result of 7. The key benefit of currying is partial application, where we can fix some arguments and reuse the resulting function. For example, we fix 3 in add curried 3 and reuse the function add 3. Now, let's take a look at an exercise to solidify the concept. In this task, we'll create a curried function that processes a list of numbers, fixing a prefix and a multiplier first. To do this, first, we defined the curried function process list. Then, using partial application, we fix the prefix as result and the multiplier as 2. Finally, we apply this partially applied function to different lists of numbers and print the results. Now let's move on to collections and callbacks. These are powerful tools in functional programming for transforming and aggregating data. We'll focus on key operations like map, flat map, fold right, and reduce, and understand when to use each one of them. First up is map. It transforms each element of a collection using a callback function. For example, given a list of numbers, we can use map to double each value, as shown here. Next is flat map, which is similar to map but flattens the resulting collections into a single list. In this example, each number is mapped to a list of 2 elements, and flat map combines them into one list. Fold right and fold left are very similar, but fold right starts from the rightmost element while fold left starts from the left. Folding operations aggregate elements of a collection. In these examples, fold right and fold left both calculate the sum of a list, but the order of processing is different. Reduce is pretty similar to folds, but doesn't require an initial value. It directly combines element of a collection using a binary operation. However, it assumes a collection isn't empty. So when should we use each one of these? Map should be used when transforming elements directly, and flat maps when each element results in a collection. Fold left or fold right for accumulation with an initial value, and reduce for accumulation when no value is needed. Let's apply these concepts with an exercise. You're given a list of students and their exam scores. The tasks include calculating average scores using map, flattening all scores using flat map, finding the total sum with fold left, and identifying the top student with reduce. First of all, we have to define the data in case class. Then we use map to get the name and average scores of each student. Then we use flat map to get a list of all the scores. We use fold left to get a total sum of all the scores. And lastly, we use reduce to find the student with the highest average score. Finally, let's discuss abstract data types. We'll cover map, set, and parallel or distributed collections. A set is a collection of unique elements. It's often used for membership testing and operations like union, intersection, and difference. In this example over here, we demonstrate these operations on two sets, producing their union, intersection, and different. Parallel and distributed collections allow efficient processing of large datasets by dividing work across CPU cores or distributed systems. In Scala, you can use .par to convert a collection into parallel collections, enabling operations like map and reduce to run concurrently. Here's an exercise to tie everything together. You're given a data set of employees. We are working with a data set of employees represented using a case class. Each employee object contains the following fields: ID, name, department, salary, and projects they're involved in. Our goal is to process this data set using abstract data types and higher order functions. First, we use the filter operation to extract employees from the engineering department who earn more than $80,000. Filter takes a predicate function which is applied to each employee in the list. If the predicate returns true, the employee is included in the resulting list. Next, we use map to transform the filtered list into a collection of tuples, where each tuple contains the employee's name and the number of projects they're involved in. Map applies a function to each element in the collection and returns a new collection of transformed elements. For example, Alice is working on two projects, Bob on one and Diana on one. Using FlatMap, we generate a flat list of all unique project names across all employees. In this case, we extract the projects from each employee, flattening all sets into a single collection. Then, to calculate the total salary of all employees, we use fold left. This operation aggregates data by applying a binary function to each statement, starting with an initial value. Using reduce, we find the employee with the highest salary. Reduce works by repeatedly applying binary function to pairs of elements, returning a single result. And finally, we use parallel collections to compute the total salary of employees more efficiently. To summarize, we've explored the power of higher order functions like map, reduce, the modularity provided by currying, and the versatility of abstract data types like map and set. Thank you so much. I used the textbook for all the information.